Tekla enthusiasts. We are back on our second session with UPB. You are listening or watching Tekla Podcast, where we are all about practical information about Tekla, how to make it more efficient and raise the efficiency and minimize the project mistakes. Today's podcast we recommend to watch from the YouTube video because we have some plugin demos we have planned, and in our studio or in our podcast we have UPB representatives. UPB who don't know yet or didn't listen to the last session, then UPB offers integrated solutions for complex constructions, steel, concrete, but also the aluminium facades that is something uncommon to do with Tekla. They're offering from design, engineering, production, and until to the installation. UPB is located, or the main HQ is located in Latvia, and they are almost 30 years old. They have more than 1,800 employees, which includes almost 200 engineers. And the turnover of 2019 was 210 million euros. That had 60% went to export, and they are exporting to 35 different countries. But today's topic that we would like to talk is about steel or aluminium facades and glass. And today we have two guests here. Artiz Aizstrauts, who is more on research, and he's head of research and development in UPB. He's probably working in UPB own concrete research center also. He has done different kind of publications. He has PhD degree, and he is giving lectures in university or college. Another second guest who we have in our podcast today is Janis Goldmanis. He has almost 10 years experience in UPB and also with Tekla. He started as a structural engineer and developed to the project manager. He's now in development project manager in UPB, and he knows a lot about this structural engineering practical side. So today's episode is dedicated to facade, to aluminium facades and with glass, and how to do with the Tekla Structures. So first of all, I would like to ask guys why UPB went to this area or to this segment of doing aluminium facades, and especially with Tekla Structures that out of the box don't have this kind of very, very much tools to work with. So
for facades, we were doing 2D design in AutoCAD until 3 years ago, when the projects were becoming larger and larger, as well as more complex. Normally for facade industry, there are these so-called system softwares, where each manufacturer of the profile system have their own system software, where you simply input the width and the height of your element window, and the software will output everything what is necessary for you. But these large projects, they normally have this problem that they require custom solutions, that simply solutions from the catalog are not good enough. You have more stricter requirements. And because of this, if we are not using system software, then we were using this AutoCAD, where everything was done simply manually. But as mentioned, the projects were growing more and more complex. And we already had a good experience when we transformed design in the frame for precast and steel from DVG to Tekla. And we decided we also have to change this design approach for facades. And we evaluated several different softwares looking at them, like Revit, SolidWorks, Tekla, CATIA, and each of them had some advantages and disadvantages. But in the end result, we chose Tekla partly because we knew it's the best, since it was the main software for our all of the other structures in holding, but also because it was very customizable. And for Tekla, there were two main benefits that we knew that worked. First of all, Tekla was capable of handling very large models, and on the other hand, these models could also be very detailed. Possibly, Tekla wasn't the best at the detailing for facades. For example, if we look at SolidWorks, where in SolidWorks it is much more suited for fabrication, but it was SolidWorks was capable of only handling one single element, while Tekla was capable of handling all of the whole model, whatever the size of it is. And at that point, when we are choosing the software, we looked at the customization possibilities through API, and we decided that we will be able to customize Tekla to the needs of our facade division at that time.
So you have done all these extra developments with the API. You didn't use custom components or Grasshopper. Everything is the advantage came, or the Tekla modeling came through your API developments.
Yeah, the short answer is yes, but it needs kind of explanation and why. The first thing is, well, in Tekla you can model whatever you want, but it's like, okay, that's good. But for facades, actually the big question is how, because facade is so much more complex than concrete and steel. It's like a way more complex. And the question is, how would you do that? What are the principles? What is the assembly? All these the questions. And to understand that, we made this, let's say, R&D team for specifically to implement Tekla in facade unit. And we made this team from Tekla experts. That's from the, let's say, we call it heavy division, which is steel and concrete. And also facade experts. So they understand what actually has to be done. And these super Tekla experts can change these things into, they understand what can we do with Tekla, and facade experts can say what we have to do. And based on these two, experiences, and we came up with let's say, a standard to model facades in Tekla. In other words, that's our view how to do things. You can do well in a million different ways, but we made this, we think that's the best way, because we had this huge experience with Tekla, well, designing by itself, and then many years experience and let's say big experience with big projects in facade division. Okay, it was in 2D, but anyway, we understand the needs from designing, and also we have our manufacturing, and also we included that thing as well, because we have to give information to the factory to produce these things. And these are the, let's say, the three main pillars to develop this standard to do this. And then when we had this standard, we made tools to make it faster, because, well, just the standard is just a document, how you manage and classify the information. And but you can do that in Tekla, well, by default settings, but it's very long time and very unmanageable, let's say that. And based on that, we understand, okay, we need to make tools for that. And once we made these tools, then we can say, okay, now we can start work in Tekla based on our standard to do things, and in much sensible way and time. That's the overall things, and Janis can go deeper in some issues and topics.
Okay, good. before we jump into the demonstration, how you are using or how goes the workflow with your tools, what do you think? How much faster now is more or less you with your tools, these kind of creating these elements and these projects than comparing to before, and what are the struggle points still that you have?
It's hard to evaluate with exact numbers, but what we know was that at the beginning, when we adapted Tekla, it was of course slower during the period at the start, but after some 3 or 4 projects, we are currently after 4 projects we knew that we are at similar speed at that time as we were with the AutoCAD, but it was day and night difference what we were actually doing. That the project sizes, how to say it, the time it takes to generate quantity takeoffs and so on, they don't rise linearly with the increase of the project. They rise exponentially. The larger the project, the harder it is to manage it. And with AutoCAD, our limits, what we were doing were projects the sizes of something like 500 elements that were manageable. With Tekla, it is now possible. We have done projects with 3,000 elements, where the project is manageable within one single very large model. And it's not the point is not the speed. The point is that we have enabled this process that we can even handle a project with the same team. We can handle 6 times larger project, and in AutoCAD it would simply be impossible. As well as the information that we are getting for manufacturing. The other stages of the construction, manufacturing, assembly, logistics, they didn't even know that the capabilities that the designers could produce this quantity of data for them, that all of the other processes can afterwards be improved in the construction cycle. And now, when we have done even more projects, we are learning better and more advanced methods, developing new tools, that also the speed increases. That I would say that now even the speed is faster, but the main important thing is that the projects that we wouldn't even be capable of doing, and this information quantity. I would also want to point the importance of this useful information. Not simply a lot of data, but information that is extracted from the model and actually used in useful ways along the chain of the construction process.
Can you give me some examples? Where do you use this information in ERP, logistics, in your production, installation? What kind of information do you use?
So when the engineers produce the model, at the very beginning, it's a very rough sketch. But this information contains, for example, the overall sizes of the elements and their locations. This data is immediately accessible to the assembly team as 3D model, and they can immediately plan installation sequence. In what sequence they want to install the elements, which facade comes first together with the project manager. Afterwards, this information comes immediately arrives to the factory, and they can plan the manufacturing processes. And they already know the rough sizes of the elements, of what profiles, what kind of bars these elements are consisting of. For facades, the material orders are very important, the schedule of them, since some of the materials take something like 3 months to arrive after ordering. And so we need this information as soon as possible. And so it's possible to extract this information and immediately also order the materials. For facades, a unique thing is that material is very expensive, much more expensive relatively than precast concrete or steel. And so we also need to be efficient with material orders for manufacturing. And from this 3D model, we can very quickly extract data about we have 20 kilometers total part length of some kind of aluminium profile. And we can immediately optimize how many bars and what length bars we need to order, so that we can now afterwards nest our parts within these bars, for example. And at any moment, the assembly sequence can change due to unexpected actions. There are always changes during facade design. And for us, this process doesn't matter, since we get these new installation sequences from the assembly teams, and we can do material re-optimizations, change the manufacturing order so that everything is done efficiently along these further stages. And this information, all of this quantity takeoffs, which stage needs to be manufactured first, what kind of quantities need to be prepared for this stage, is done automatically. Then compared to AutoCAD, where somebody would have to look at the facade drawing and do manual calculations, how many of what are in this particular order. And not to even mention the quantity takeoffs overall, compared when we are looking at BIM model, how easy it is to generate quantity takeoff, and when we look at the DVG. For precast panels or for steel, it is a little bit simpler. You simply have your main beam profile. You have this length of the profile, which you add together. Or for precast wall, you simply need to calculate the total volume, and the hardest part would be generating bending schedule. For facades, meanwhile, you have this unitized element. It consists of something from 200 to 400 unique parts. And you have to calculate how many of what parts. They are very widely different. A lot of small interlocking pieces, and you need to know how many and where they are located in it, which elements they are assigned to. Previously, I would say, so I think we had calculated that quantity takeoffs for DVG 2D planning took something like 17% of engineers' time. Simply generates the quantity takeoffs. While in Tekla, it's almost immediate, I would say. So we are taking this data and pushing it into ERP system for the purchasing department.
Yeah, especially if there are any changes, then you are doing the job again. So it goes crazy. Okay, so I'm very interested of seeing a demo and hearing how you are doing these kind of like facade elements in Tekla Structures in UPB. Can you give me a short demo of how it goes?
I would say I will show a demo of our tools that we have developed. I suppose you can imagine that normally you can simply open Tekla software and manually draw some beams. And instead we have developed a set of tools how to quickly push more highly detailed information into Tekla. So design normally for facades starts with a 2D sketch in DVG, where the design engineers have developed this sketch. And first step for us, we need to get all of these unique profiles into Tekla. Since Tekla, of course, normally it's a catalog consists of the normal double T beams and so on. For facades, each project consists of these unique cross sections. And we have developed this tool where you can simply import multiple DVG files, which consist of these unique cross sections. We find unique blocks that you have in these files, as well as provide functionality to make them a little bit less detailed, since when you will have your very large model with multiple hundreds of thousands of these parts, every little line counts to make them a little more simple ones. And after the push of a button, all of these cross sections at the same time is imported into Tekla. Afterwards, you need to generate your main frame of your building. There are two types of stick facades. First are unitized element facades, and the others are stick facades. And for us, by far, the largest quantity of what we do is unitized element facades. And so for them, we have developed the most robust, advanced tool, which is called unitized element, within which you can define all your frame geometry so that you don't have to do it by hand, drawing these separate pieces. And the interface is relatively easy. You simply choose where and what you want to split, as well as modifies the dimensions, and you get what you need. And this is intended that you look at also at your drawings, what the engineer has designed, and you recreate it in Tekla. And afterwards, you can also save it as a library file and copy it in hundreds of places, however is necessary. Meanwhile, for stick facades, they are normally not as unitized. They are simply, your whole facade is one large assembly normally. And then for this type of thing, we have developed a direct modeling tool. It's intended that you have your reference in the background from the architect, where it's already decided where your aluminium profiles need to be located at. And then there is also similar, that you can simply select where you want your beams to have, where you want your beams to be. And there are several options how to do it. You can either simply click spaces one by one, or you can generate an array of beams. And as well as there are automatically different options for vertical and horizontal sticks, since oftentimes they have these profiles. The idea is also to quickly generate your whole grid of your load-bearing aluminium profiles, and then also, of course, adjust some attributes or parameters, how they are rotated and so on. And of course, you can also do it by hand during this process. You can simply, the first thing, of course, you generate this cross-section in Tekla, and then you can also repeat this process by hand without any special tool. But what our tool enables is that you afterwards have dimension control of all your openings. How near is adjacent beams? At any point, you can see these dimensions. Next thing is also splitting your beams. You can either automatically split at some kind of a point, or automatically split the horizontal beam at all of the vertical intersections, so that you can quickly generate these individual parts by just sketching your whole facade. And so here you already have your, I would say, low level of detail stick arrangement of vertical and horizontal sticks. You can click on any stick, see these dimensions, and if necessary, you can also, of course, adjust them by this direct modeling controls. As an example here, click on a beam, click on a dimension, adjust the size of the dimension, the beam will be adjusted. And you can do these micro adjustments, or you can do global adjustments for this whole facade, for example, changing the material, the surface treatments, and so on of these profiles. Next steps is adding additional complexity to these profiles. Since this is only load-bearing profile, but the facades consist of a lot of different parts, so-called profile sets, which is gaskets, glass covers, and other different profiles. And what we do is we have developed a tool where we can take this 2D DVG detail, import it into our tool, and we will find what kind of blocks you have in this DVG file, and automatically recreate the situation in Tekla, so that you don't have to draw these beams one by one, but you have them positioned the same way that you have them in DVG. And afterwards, you can adjust all of the attributes, start positions, numberings, materials, and so on, and save it as a library file to afterwards add it everywhere else where you would want to have. And here you can see with a click of buttons, I quickly change these detail types that I would want. And then there are different ways how you can insert. You can insert it quickly, either along the whole length of the element, or you can also choose some kind of intervals where you want to insert this more complex, this complexity on top of your main profile, your main part. Or simply, for example, along the whole length of your facade. It depends of what kind of detailing you want. Is this low-level sales detailing, where you can have one very large beam across your whole facade, or you need a very highly detailed for manufacturing, where everything needs to be exact with the end finishings and so on. And again, it's a matter of a few buttons, you can change it to different types. So using this tool, you can quickly get all of your bar profiles, gaskets, and so on into the model. I'll spend some more time adjusting it. Here you can see that I have previously copied out from my main design file these vertical and horizontal profile sets. I'll quickly adjust them a little bit. And so that it looks good for the purpose where it's meant to be. And afterwards, I add it in, copy it in other places where it's necessary, and so that I can do further detailing of this facade. So, but it should be as simple as this. Next comes joining these profiles together. So first of all, adding the correct horizontal profile set. Again, it's simply choosing the files from your library instead of generating them by hand again and again. As we, our philosophy is that information should be generated once. And here, the design engineer has already generated information of what your detail should look like. And we are not recreating all of these positions by hand in Tekla. We are taking the source of this DVG and simply transforming it from DVG to Tekla. This, I would say, now is relatively low level of detail of facade, where we have these profiles and they are somehow like without connections, without fitting, joined together. What we can do now is we have developed a tool that quickly creates the correct fittings so that we get a higher level of detail. And for most profiles, that is everything that you need for LOD 450. For these load-bearing profiles, you need custom connections, while for these other external profiles, usually you simply need to fit them with correct angles together. And we have developed a tool that works. It works either with our components or it works simply with separately drawn Tekla parts. It doesn't matter how you have gotten these parts in Tekla, but you simply select one batch of parts, you select a different batch of parts, and this tool will pair them together. By default, it matches parts together by its profile, while you can also set up custom pairings. One problem is that all of these profiles are named by their articles, which are simply a string of numbers. And even designers often get lost which is which. And we have developed a visual system where with the mouse over we show which particular bar it is in the model. You can choose them. You can adjust the connection type, if it's a perpendicular or it's along the bisectors of fitting. And you get your correct net length of your profiles, which will be necessary for the cutting processes. And afterwards, it's also joining together the profile sets with various situations. So first of all, it is a tight fitting right along this main vertical bar. And otherwise, it's also possible to adjust these positions offsets to what would be necessary. And you spend some amount of time generating settings for your connection in one single place like this. It took, you see that this is like almost without any speeding up. It takes something like a minute to set it up. And afterwards, you can copy it to all of the other situations where it replicates. Since unitized facades, they have these custom solutions, custom profiles, but the connections are usually repeating in some kind of pattern in a lot of places. Some normal stick facade connections, they have some connections are repeating in thousands of places. And then it's a matter of process how we can quickly insert, copy these settings to all of these other places. But you don't recreate the information. You create information once for your detail, and then you repeat it everywhere else. Then for facades, one of the major topics should be insulated glass units, insulated glass packets, where we have a tool where you define the perimeter of your beams, which can be non-regular shapes, and it inserts this packet, and then it's simply defining the positional settings as well as the packet structure itself. Here you can see that I try to replicate this drawings information, how it's positioned. Here it's visible in older version. We have since upgraded it to a more intuitive one so that I don't have to try out minus and plus values. And as well as you can see the speed with which I can adjust the structure of my packet, the sizes of the voids and the layers themselves and so on. And afterwards also, I generate these settings once for this type of a packet, and afterwards it should be easy to insert this type of packet everywhere else where it's necessary. And then it's this additional detailing. For the packet was already introduced in this places as necessary. Then for windows, for example, if you have a windows that can be opened, it requires additional parts, and then you can create it modular. That with one input you insert some information that is almost everywhere, and then for some openings you can insert more detailed additional information about the window accessories. And then there are different types of fillings. For example, one was this insulated glass packet. Another type that we often encounter are bent sheets as covers for insulation. And I would say it's easy to make it as a custom component for fixed situation, but these custom components are hard to adapt for different cases. If you have, for example, 4 edges, 5 edges, or 6 edges, and possible non-regular corners, all of them adjust. While with plugins, it's easier to ensure stability, that they are working from one model to another model. So, and with such modular steps, as an example, we can recreate the facade with the detailing level that's necessary for us, adding custom components on top of it. Additionally, we try to ensure that our plugins work with more advanced optimization methods, as like, for example, Grasshopper, where Grasshopper is very good at, first of all, generating some unique organic forms. Here I will show an example where I generate a Voronoi pattern, for example. It's quite easy and quick to do. Of course, it's harder to replicate something that the architect has already done, but if you want something weird, then you can easily create it yourself, for example, like this. And then we can combine together Grasshopper with our plugin to very easily recreate this packet type that we want to within these openings. And if we calculate that we, for example, need some different thermal resistance or something like that, we can simply change the catalog entry and immediately update all of these packets like this. And we get this detailed model with the push of these buttons. Since then, what we have done, we have made these, since the creation of this video, we have made these packets more with a higher LOD, inserting also the spacers so that it looks better. And we are also now trying to push this workflow where you are working with the whole facade at once, also for normal engineers. So they have scripts and applications available where they select the whole facade and something's being inserted, and it is also joined together with calculation.
How fun it was doing at first these facades without any these kind of developments, one by one, manually doing these beams and columns and the connections. That I think I would go crazy, but in this demo it looked really easy.
Well, it was a lot of experimentation with the correct approach. Howard previously mentioned we have developed this standard, but in order to develop the standard, we had to go through different iterations of models, different projects, where we tried different approaches. At the very first model, for example, all of us were Tekla experts, and so we decided that Tekla's custom components are quite good. We will simply generate very super complex custom components. But that didn't work, and we had to finish the project with manual methods. And then with the next project, we decided, okay, the Tekla custom component doesn't work as the main frame of the element, but we can instead, the process itself is good enough. We will simply replace this custom component with a plugin. And we know that the plugin was good enough to accept all of this other inputs in order to be stable and good working and be parametric.
As I understood, now these plugins have been done with the OpenAPI. So, and you mentioned that the custom components were not enough at some point. Can you tell some recommendations, or until what point you still think that custom components are good, and from what point you prefer or you recommend to go to OpenAPI?
So connections should definitely be custom components, since they are unique from project to project, and it is almost impossible to make a comprehensive plugin that solves everything. The connection creators that was shown in the demo, which made these fittings, it's also the purpose is only to make fittings. And if you need to do some custom bolt connections with inside connectors, the idea is that you make it as a custom component and then you import it within this tool. You should definitely think about doing plugins if you have a creation criteria. With some places you need to create something, and with other places you don't need to create something. For example, this unitized frame, normally for unitized elements, they look the same, but they have some kind of a small difference. For example, every second element possibly doesn't contain middle vertical beam. And although it sounds in theory, this idea that something is created for one element and something isn't created for the next element, it's either two different custom components, or it is a plugin that can handle all of the cases. It shouldn't be one complex custom component that can interact. And also a very big no-no is parametric custom components within parametric custom components. It will collapse very quickly. Your project will stop working as expected. And these facades are so complex that at the very beginning, it was the only choice how we could solve this parametric facade somehow without any other tools. We had to make these components within components. End result was that we had to explode everything and do everything by hand. It was a painful mistake that we learned.
That's good to learn from others' mistakes and not do them ourselves. One question that I got through my mind is, can you tell more or less how much time or effort have you put on these custom components of or these API plugin developments?
It's more or less about 4,000 man hours. It's something about that, and it's in hours, and time is like, I don't know, 3 years maybe. If we take out this huge experience in Tekla or facades, well, you can't do that just with developers like random development company. I would say the developing part is the easiest. That's just like programming, and it's no big deal. But the biggest issues probably was, with these things, how to do this. As I mentioned before, this standard thing. What is the assembly? What is the component? What is the plugin, and so on? And well, as Janis mentioned, well, at the beginning you think, that should work because it worked with steel or concrete. But as he said before, one element in precast wall is like, I don't know how many detailed in-cast details, like 20 max, if we don't count rebars by each rebar as an item. But in facade element, it's 200. And even the halls and so on. So the usual approach works on the paper, but in reality it doesn't work. So that try and error and try and fail was the actual the only way to go. And I think this R&D part was the crucial and most difficult.
Yes, I can imagine similar kind of stories I have heard in other places also, even if when someone is doing e-shop, for example, my friend was doing, and then he invested a lot of money of creating themselves one e-shop platform and many thousands of euros, and in the end somebody came and asked, like, okay, why didn't you use the ready solution? They're a big team behind that, and they're improving it every daily, and it's in the end it goes much cheaper, and the updates also. So she went also on this like ready-made solution. So as I understood, these tools are also available in warehouse, or where people can get these tools. So is it available somewhere for other?
Yeah, we have published them on Tekla Warehouse, and there's also a lot of videos and also a lot of manuals how to work with them. And at this point, we have like testing phase to calibrate it and adjust to different business approaches. As I said, before we made the standard and these tools based on several other company experiences, but mainly on our, and we have to understand whether it works completely with every possible company, well, in the world. So yeah, they are in Tekla warehouse.
And right now, what do you think? Who would be the customers or the companies who would benefit from these kind of tools the most, and who should definitely go and check them out?
The most beneficiary would be companies who have just who are trying to transfer from 2D DVG to Tekla, or from any other software that they come to Tekla, since they don't have to figure out things themselves, the very basic things. For example, how to draw this insulated glass packet. They already have this tool where they can quickly, very inexperienced user can take the tools and generate already relatively complex facade in an easy amount of time. Since and also for more advanced companies, it would be helpful, because other alternatives are that you need very experienced users who are capable of creating quickly complex custom components to replicate the same process that we are doing with these components, with our plugins. And we are, what the tools achieve is lowering the bar of entry, the qualifications of the users necessary. Since for precast and steel, I would say the bar is much lower. How qualified engineers you need in order to generate optimum workflow. For facades, it is much higher, and these plugins lower this.
Definitely, I would recommend also to go see these warehouse tools. They all have separate videos how to use each tool, and then good documentation. So test them out and let us know how it worked. For the last question, do you have any recommendations how these Tekla engineers can reduce their mistakes more even and raise their efficiency? One thing is to use, of course, these tools, but do you have any other kind of recommendations that you think that would help to reduce project mistakes and raise the efficiency of how fast they can get these results?
Mistakes could be eliminated if you don't try to do something more complex if you haven't learned how to do something with simpler methods. So how to say it? First of all, you should really learn Tekla's basic functionality, like do something manually. Next step would be that you learn how to do automatized Tekla, how to make custom components, but still like simple custom components, like simple drawing templates. When you have learned that one, only then you should take the next step, how to create parametric custom components. And with time, possibly then also introduce how to use Grasshopper to automatize this insertion of the parametric custom components. And each of these steps, like no matter the method that you do, you should make them simple ones. Separate your workflow into simple steps. Don't create one super custom component or super Grasshopper script that does everything, since it will be very hard to debug it, understand the mistakes within it if something's not working as expected. Instead, separate everything into small modular steps, separate small custom components that combined together achieves what is necessary for you. Similar approach is for these our facade plugins, that we don't have like one button and everything happens. Instead we have these separate steps: generate the frame, library item, and copy this frame where it's necessary. Add these profile sets on top of it, add separate glass packets, and when combined together, you have your higher level of detail facade.
Do you have any final recommendations or wishes for our Tekla warriors?
I would recommend to never stop improving yourself. That the more you learn, the more you understand how much you don't know yet, and that's applicable for any step. That anything that you do in Tekla that you think is possibly like repetitive or like inefficient, most probably there's some way how to solve it, and most probably somebody has already solved how to do it more efficiently. And you simply have to reach outside of your comfort zone and learn this method how to do something better.
Okay, thank you very much, Artis and Janis. Your information was really useful, and hopefully it helps someone to be more courageful and go with the Tekla Structure, also do the aluminum facade. So if they already have been trying, then at least definitely go and try out your plugins. And I wish this on this way many luck for the users and Tekla Structures engineers, and it's not so complicated anymore as I at first was thinking. So have courage and jump in. Thank you very much, guys, and take care.